Hello and welcome back to Russ's Movie Corner. My name is Russ, and as you can see, I'm sitting in front of my movie corner. I have my Son of God movie and my Guarding the Galaxy t-shirt on, which means it's time to take down another atheist. This is part 2 of my Comments on Comments episode, taking down a guy named Turbo Brain, who doesn't really have a turbo brain, as we've seen in the previous episode. Now, I went ahead, this is kind of towards the end of everything. I don't know why it went down that way. So when I last left off, we had just talked about, right up here, we had talked about Turbo Brain's comment on how Ramesses II was listed as the oldest pharaoh, having lived at 86, and the first pharaoh was at 3,297 BC. Which I said that, I said that he basically owned himself because he said, because of flood, if we take from basically around the time of Jesus' birth, and then we go the 400 years back to when Micah was written, and then we take those dates and we go back all the way up to Adam, we know approximately when the flood was. The flood was at about 4400 BC. Okay? So, it is possible for people to live to be 900. The thing is, something changed after they got done with that. Okay? I also mentioned that this particular person was not paying much attention to other things that was going on. Okay, he's also going to make some grandiose claims. Okay, and this episode is going to get very technical very quickly, because now we're actually going to start to get into some geology and some physics, okay? So I hope you're strapped in, buckled in, ready to go, because here it is. So, when we last left off, we were right here where my cursor is. So then, I had talked in my video, this is a rebuttal, so this is in response to a rebuttal video that I did about Simon Dan and Kent Hovind and some of the other things. And I had mentioned ice cores. And ice cores are not what people think they are. Because as I said in my video, okay, when they drill down into an ice core, okay, they basically, they take that ice core, okay, and then they drill down and they take a core sample from the Earth, okay, and then they take those two and they match them up, and they say, okay, so we see the thickness of this layer here, we see the thickness of this layer here, those must be the same, and those are at, 300 years ago. And so then we come down to this one, and those are at 500 years ago. And then we come down, to this one is at 1,000 years ago. And this one is at 10,000 years ago. And this one is at 50,000 years ago. And this one is at 100 million years ago. Okay? Ice cores do not tell us ages, because they're basing it on the layers of dirt. And again, the layers of the dirt don't even tell you what the age of the Earth is. Okay? So for this guy to stand there and say, wrong, ice cores do tell you ages you don't know, he is completely ignorant about what geology actually is. Okay? So then, because I told him, I said, no, son, you cannot, and I told him that. I basically told him the same thing I just told you. They match up dirt columns and ice columns, and you don't think that it doesn't, like ice doesn't, you don't, like they only have one freaking snowstorm in Antarctica every single year? Like, literally, think about that for a minute. Does it just have one massive ice that just dumps all of its snow at once and then it's done for the year? No. It dumps continuously down there. Okay? All throughout the winter. In fact, people that have been down there will tell you, yes, during the wintertime, it is deep. Like it is, the snow piles up. And even, it's wintertime here where I live, and we actually have snow on the ground, which is a first for us living where we are. In a long time, probably about 20 years, we haven't had anything here. Like we haven't had snow on the ground in December in a long, long time. And generally, if we do have a snowstorm, we have like about maybe a quarter to and a half an inch. And this winter, we had about 5 or 6 inches, which is kind of a record for us in December for a long time. And now it's kind of knocked back to about 3 inches on the ground and like kind of like a sheet of ice. Okay, because people drove on it, and and it's just and it's been very cold. And so it's like, yeah, you sit there and you go, And if you look at the layers of snow, you can see that those layers build up. Because you can tell the difference between the first snowstorm we had, which dumped about 2 to 3 inches, like 2.5 inches. And then we had another snowstorm that dumped about 3 inches on top of that. Okay? And you can tell the difference in the layers. Okay? There's 2 distinct layers because the first layer fell and it compacted down a little bit. Okay? Then the second layer fell and it compacted down a little bit. Okay? So if you have, 10 or 20 snowstorms in a year, like you do either in the north or in the south at the poles, you'll get, 20 or 30 layers of snow built up. Okay? So you can't tell me that they know exactly how old the Earth is by counting the snow layers, okay? What they do is they do the same thing that they did in geology. They just count, okay? And they think, oh, okay, well, we know that this layer is this many millions of years old. We know that this layer is this many millions of years old. Well, how do you know that those layers weren't successive snowstorms? That's the problem. Okay? And then this guy, and then he says, and you study geology? Really? Antarctica is known as the largest desert on Earth. They look at ice cores, thousands of feet deep, not snow cores. What do you think ice cores are? Like, literally, what do you think ice cores are, dude? How do you think they got there in the first place? You see the level of ignorance, willing ignorance you have to deal with when you do this stuff? Where do you think the ice comes from, son? Do you think it just all of a sudden decided one day, hey, I'm just going to freeze? Like there was just water down there and then all of a sudden it just decided to freeze? Where do you think it came from? My God, are you ignorant? All right. Then he says, and yes, I have studied geology in the field, okay? This is my actual field notebook, okay? There's my name, okay? And then this is where we studied. We went to Bishop, California. You can actually drive down there and you can actually go where I went. We went to 3 different places. We went to Fish Springs, and we went there for like 2 or 3 days. And then we went to Big Pine. We went there for, I think the first one was 2 days. The second one was 3 days. And then the final one was like 5 days. And that was Pulley to Folds. And that one was the longest one, okay? And the most detailed notes from that one. But basically, when we got to Fish Springs, first day, okay, the professor that I had, okay, he's quite a famous geologist, okay, at least he was back in the 90s and early 2000s. I had actually seen him on television before I went to college. I'd actually seen him doing a video on or he had been interviewed about some earthquakes down in California, some faults and stuff. So he has studied a lot of folds and faults down there, okay? And he's actually, one of the guys that I actually asked one time. I was like, hey, professor, if, let's say somebody's, doing a bunch of papers, for peer reviewed, like, do you do peer reviewed papers? And he goes, yeah, I do. And I said, well, do you read them? And he goes, not necessarily. He goes, I'm so busy with my own stuff, I don't always have time to look at it. Because I read the basics, the summary, and then I will flip to some of the data tables just to make sure that they've done everything all right, and then I'll send it back if they need to do something. And he goes, now if I see something that I see that is like, whoa, this might be off, like we might need to do something here, then he'll actually sit down and read the whole paper, and then he'll like contact that person and say, hey, it looks like your conclusion might be wrong on this, blah blah blah. But he goes, generally speaking, I only get to read just the summary, and then I'll look at the data points just to make sure that they've done everything, and then send them a couple of suggestions or just give them a thumbs up. And that's why I call it a backslappers club, because people don't understand that when you're a professor, okay, at a university, you are so busy with your own research, and you have graduate students, and you have other things going on, that you don't always have time to sit down and read the thousands of peer-reviewed papers that are sent your way, or papers that people want to be, quote, peer-reviewed, okay? So you're not necessarily going to be able to sit down every single day and just read through the hundreds of submissions that they get, okay, if you're a professor. It's not going to happen, okay? But these people take such a big, thing on it that it's crazy. But anyway, so the first day we were down there, we went up to a cinder cone, okay? And there was red rock. The cinder cone was just basically red rock, and he walks us up on this thing he called the saddle, okay? And basically, we were standing, okay, right here. And we were standing on this little ridge, okay, and below us was this big hill of black rock. And it came up to a certain point. And then behind that was red rock. The same red rock that was of the rock that was on the cinder cone itself. And then it went down this hill into like a little valley where there was a mix between the red rock and the black rock, and then you had the actual cinder cone here, okay? And so the professor kind of had us walk up there, and he goes, I want you to figure out what happened to this thing, because I'm not going to tell you. I'm going to tell you tomorrow, but I want you to just kind of puzzle it out in your own head. So we scrabbled all over this thing. We looked at all these different rocks. We were looking at different things. We were like, what in the hell? Because we're brand new to this. I mean, we're students in a Geology 200 course, okay? Kind of standing there going, is this, where are we? Like, and so the next day we came back out, and he goes, are you ready? I'm going to tell you what happened. So, where we were standing on this little ridge where there was black pumice, and then there was mixed, and then there's the cinder cone with the red pumice. He goes, the black pumice and the red pumice are all the same. The red pumice was oxidized, okay? That means that oxygen actually changed the sulfur and the iron in it to that reddish color, okay? But they were the same rock. Literally. Just one's black, one's red. He goes, what happened is here's the hill like this, where we were standing, okay? And then a fault did that, exposing the black rock underneath. So we had red rock, black rock, and then up the cinder cone. And so literally, this fault literally shifted the hillside down so that you had this part that was normally, he goes, if you were to dig through the side of this hillside of this cinder cone, he goes, we won't let you, but if you were to dig through the side of that cinder cone, you would eventually get through enough layers of the red rock that you would hit the black rock. And he goes, if I'd let you do that, you'd have figured it out in 3 seconds. You'd have gone, wait a minute. Then that must have just been something where it just shifted. Okay? So, that's literally what we did. Okay? And I'm going to get back to the rest of it in a few minutes. Okay? Basically, I just kind of wanted to explain that. Okay? That I have actually been out in the field. I have actually studied geology. In fact, my Geology 101 professor, okay, had gone down to Antarctica. And he had told us a story about how they went in and how they were drilling for ice cores and how they were doing things like that. So yeah, I do know about ice cores, okay? And literally, they try to monitor how much snow falls because they need to know how thick the layer is so that they can determine the ages of the layers in the ice cores. But even then, they're still just matching them up, like looking at the dirt layers, and they're going, well, see, this dirt layer is this thick, so this must be this layer, which is this thick, and this. That's what they do, man. Okay. Then when I talked about the Hoven theory, okay, where, you know, he talked about the 3 fingers thick sheet of ice, okay, that was, you know, so many miles up around the Earth, okay, canopy. This guy goes 3 fingers thick and 10 miles up. Where's that in the Bible? Well, okay, you wanted to know. Here it is. So, in the first one, we see in Genesis 1:6, it says, then God said, let there be an expanse in the midst of the waters, and let it separate the waters from the waters. God made the expanse, and separated the waters which were below from the waters which were above the expanse, and it was so. God called the expanse heaven, and there was evening and there was morning the second day. It says, let the waters below the heavens be gathered into one place, and let the dry land appear, and it was so. And God called the dry land earth, and the gathering of the waters he called seas. And God saw that it was good. Okay? So that's what Kent was basing that on. Okay? And the next part is in Psalm 104. And it says, in Psalm 104, verse 5, he established the earth, God established the earth upon its foundations, so that it will not totter forever and ever. You covered it with the deep as with a garment. The waters were standing above the mountains. At your rebuke they fled. At the sound of your thunder they hurried away. The mountains rose, the valleys sank down to the place which you established for them. You set a boundary that they may not pass over, so that they will not return to cover the earth. Okay? And then in verse 10 it says, he sends forth the springs in the valleys. They flow between the mountains. They give drink to every beast of the field. The wild donkeys quench their thirst. Beside them the birds of the heaven dwell, and they lift up their voices among the branches. He waters the mountains from his upper chambers. The earth is satisfied with the fruit of his works. So basically, what Ken Hoven is saying there is, in verse 6, where he says, you covered it with the deep as with a garment, the waters were standing above the mountains. At your rebuke they fled. The sound of your thunder they hurried away. The mountains rose, the valleys sank down. So that he's basically saying there that was geology basically changing the earth after the flood. Okay? And that's kind of what Kent is talking about. Is he's saying we have this, there was something up here that was watery. Okay? That went away. I'm not sure what it was, but it was containing everything. Okay. Then he says, the ideal gas law says that pressure is inversely proportional to volume, so air pressure would increase by 216 times. Okay. This is where it's going to get a little technical, people. If you're not up on your physics or your trig, this is probably going to go shoo. And I expect Turbo Brain to just not understand this at all and just completely bypass this whole entire thing because he's going to go, uh-oh, I don't really understand this. Okay, I need to come up with something else. The ideal gas law does not say, okay, it does not say that the pressure is inversely proportional to volume, so air pressure would increase by 216 times. The ideal gas law actually says, and this is from an actual, and again, I will post the links in the description. The ideal gas law, this is from an actual physics college physics website, okay? The ideal gas law, also known as the general gas equation, is an equation of the state of hypothetical ideal gas. Although the ideal gas law has several limitations, it is a good approximation of the behavior of many gases under many conditions. Benoit Paul-Émile Clapeyron stated the ideal gas law in 1834 as a combination of the empirical Charles law, Boyle's law, and Avogadro's law, and Gay-Lussac's law. The ideal gas law states that the product of the pressure and the volume of 1 gram molecule of an ideal gas is equal to the product of the absolute temperature of the gas and the universal gas constant. Okay, so the empirical form of ideal gas law is given by PV is equal to N times R times T, where P is pressure, V is volume, N is the amount of substance, and R is the ideal gas law. And also T being temperature, okay? Because that's the temperature of the gas, okay? And basically what this means is that when you subject the gas to a certain amount of pressure, okay, contained in a certain amount of volume, okay, the ideal gas constant and the temperature will give you what that pressure and volume will be, okay? Okay, and the ideal gas law units, okay, R is 8.31 joules per Kelvin mole, or molecule, okay? So it says when we use that one, then we have to plug the pressure P into the unit of pascals, or PA, volume into the unit of moles, and the temperature T in the units of Kelvin, K. Okay? So basically, when we measure pressure, and this is something that I studied at my technical college, okay, when I studied physics, because we had to know pressure, because as an instrumentation technician, we studied pressure, okay? So you'd have pressure in a tank, and so we would need to know what is that pressure, okay? And we would generally use the units of pascals, okay? Or we'd use either pascals or we'd use pounds per square inch. It depends upon what you're trying to do, okay? But it says when we use the gas constant of R is equal to 0.082 pressures of atmosphere per Kelvin molecule, then the pressure should be in the units of atmospheres, volume in the units of liters, L, so it's liters of atmosphere, and the temperature T in the units of Kelvin, K, okay? So that's when we're talking about like actual like the air surrounding me right now, okay? That is somewhat pressurized, Okay? And because of our construction materials and because of things, there is an exchange of air molecules that happens, but it's very, very small, okay, from your house to outside. Generally speaking, when you open a door or, like, you have certain things happen, that happens. But it's not under, like, we're not in a pressurized container. Like, I'm sitting in my living room and it's not a pressurized container, okay? But the amount of air that's in here might be different than the amount of air that's outside, okay? But it's not pressurized, because I'm just talking about the amount of molecules. It's not pressurized to a point where it's causing me to have problems, right? Because I don't have to have some kind of an oxygen filter to scrub out my CO2. Like, I don't have to have plants to scrub out my CO2, okay? Because there's enough exchange that oxygen is coming in, CO2 is going out, and so I don't have to worry about my atmosphere becoming toxic, okay? This is something that they have to care about when, like, they're, like, the Artemis 1 mission, right? Or the Apollo missions that went to the moon. Those missions, those guys had to worry about that stuff because they are in a pressurized container, okay? But you have to remember that this is something that only happens when, number one, you have a certain number of pressure, you have a certain amount of pressure of air molecules. And number two, it's only on paper because there's so many variables to consider that this will never happen on Earth or anywhere else. It's only on paper, okay? Because there's so many variables, okay? So, what it is, okay, how it works, okay? This is how Mr. Benoit Clamperion derived the ideal gas law from Robert Boyle, Gay-Lussac, Amado Avogadro, okay? So he took Boyle's law, okay, Charles' law, and Avogadro's law, okay? And so volume is proportionally equal to the amount of pressure, volume is proportionally equal to the temperature, and Avogadro's law is volume is proportionally equal to the number of molecules of said gas in a contained space, okay? So combining the three expressions, you get volume is proportionally equal to the number of molecules times the temperature times the pressure, okay? So as the above equation shows that volume is proportional to the number of moles and the temperature, while inversely proportional to the pressure, okay? So by multiplying both sides by P to clear off the fraction, because I didn't get, when I copied it down, it didn't actually, because here again, when you go to the website, you'll actually see that it's actually NT divided by P. Okay, so then if we multiply both sides by P, okay, then we get PV is equal to nRT, okay, which is the ideal gas. So, it says, what is the gas of volume, or what is the volume occupied by 2.34 grams of carbon dioxide at STP, okay? So, we have volume is equal to nRT divided by P, right? So, we throw in all this stuff and divide it, and we get 1.19 liters, okay, at 2.34 grams, okay, at 44 grams per mole, divided by the, multiplied by the constant, and then multiplied by 273 Kelvin, which is like room temperature, basically. Okay? And then it says, calculate the temperature at which 0.654 moles of neon gas occupies 12.3 liters at 1.5 atmospheres. So then, by solving the equation for temperature, okay, then we plug in the 1.59 atmospheres, we get the 1.23 or 12.3 liters. divided by 0.654 moles, and then you get, yeah, and I guess I didn't get the thing, but anyway, you'll see it down there. If you go down and click the link, you can go there and you can look at it, okay? So, the relationship between pressure and temperature. So the graph here shows the relationship between temperature and pressure for different gases, okay? So it says on extrapolating this graph, we see that the graphs always intercept the x-axis, okay, at a point we now call absolute zero, which is negative 273.15 Kelvin, which is different than Celsius, okay? That's like thousands of degrees Celsius. It's like, yeah, it's like, because you can see here that 100 is Celsius, okay? I believe that's 0 degrees Celsius. Yeah. Yeah, 0 Kelvin is equivalent to negative 273.5 degrees Celsius. Okay? Now, absolute zero has never been reached. Okay? So it's like, yeah, it says as the molecule gets colder, its energy and consequently its movement and vibrations decrease in amplitude. As we continue cooling it, at some point the atom will reach a state of minimum internal energy where the atom has lost almost all of its energy and is stationary. So here's the interesting thing, okay? The measure of temperature is basically the measure of how fast molecules move. The slower the molecule moves, okay, the less thermal energy it has in it. And what they're saying with the ideal gas law here is that as pressure increases and as temperature increases, the amount of excitation, okay, of the molecules goes up. Okay? Because they can move more freely. Okay? But as we lower the temperature and as pressure lowers, okay, that gas starts to settle out. Okay? And that's what the ideal gas law deals with. Is it's basically saying, look, if we look at this, it just goes straight back to absolute zero, where nothing moves. Okay? Like, it would be completely just gone. Okay? So, yeah. People need to realize. So here's the thing. Okay, some frequently asked questions. What is the ideal gas state? It's where the pressure, temperature, and volume of a gas are related to each other. It has nothing to do with, oh, if I had, this at this gas would just blow something. That's not how it works. Okay? The pressure of a gas in a pressurized container has nothing to do with the ideal gas state that it's in. Okay? Because you're talking about looking at our atmosphere as it is today and trying to compress all of that down into something. Okay? When I'm saying that, our atmosphere, okay, and that shell could have been a lot larger than it is, okay? And I could have maybe misheard Kent Hovind, and maybe he said 50 miles up. I don't know, okay? But all I'm saying is that the ideal gas law, okay, because this is the one thing that this guy doesn't know about, okay? Why is the ideal gas law inaccurate? Only under perfect conditions is the theory of ideal gas is valid. The ideal gas law effectively fails at high pressure and low temperature because the molecule size and intramolecular forces become important factors to take into account and are no longer negligible. Ideal gas law doesn't apply to liquids. And it says, how is the ideal gas law used in everyday life? Assume an engineer wishes to store 500 grams of oxygen in a container at 1 atmosphere and 125 degrees Fahrenheit. The ideal gas law is used to determine the capacity of the container that must be constructed for the same. It has nothing to do with, oh, if you had this much, if you had a 3-finger thick sheet of ice at 10 miles, man, that would just, that would make this pressure this. You don't know that. Because you can't know that. Okay? Because the ideal gas law doesn't state that. The ideal gas law only says that when you have a certain container under ideal conditions, okay, we can put it there. And God is God. He could hold that shell together just by the sheer power of his omnipotence, okay? He's God. He can do whatever he wants because he can make the laws of this universe bend to his will. He's God. Okay? I mean, but the way that this guy made it sound, okay, with his comment over here, okay, where he says, that says that the pressure is inversely proportional to the volume of air. No. Pressure and volume are directly tied. They're not inversely proportional to volume. Pressure is not inversely proportional to volume. Pressure and volume are the same. Okay? Because to know the volume, you have to solve for V, which means you have to divide both sides by P. It's not inversely proportional. Okay? If anything's inversely proportional, it's the number of molecules is inversely proportional to the pressure or volume of a space. Okay? So no, that's not how it works. And then he goes on to say, because I had seen this comment, the 3 fingers thick, 10 miles up, blah, blah, blah. Then he says, I see you don't use the proper Bible version. Ken says that the KJV is the only real inerrant word of God. My response to this was, who died and made you arbiter of what Bible version to use? Son, you're not even a Christian. You're not a Bible scholar. Okay? Neither is Ken Hovind. I have a book written by a PhD, okay, that tells me that it's okay to read different versions of the Bible. I've also read a parallel study Bible. That is, or a comparative study Bible. It's basically what it is. They call it the parallel version. They put the King James, the New American Standard, the NIV, and the Amplified side by side. Okay? And while, yes, some things have changed in terms of wording, maybe sentence structure, the meaning behind the words hasn't changed. Okay? And that's what we know as Christians, is that it's not about what version you use. It's about the meaning behind the words. Okay? So if you've ever had that one English teacher or English professor who sat there and said, you need to see what's behind the words. You need to see the meaning of what they're trying to say in this passage. That's what we're talking about. Okay? Look, Kent can say whatever he wants. I've had people tell me that the only way, because the Mormons say, only use the King James Version. The Jehovah's Witnesses say that their version, their New World Translation, I think it's called, is the only Word of God, even though they changed way more than anyone ever thought to change in a Bible for like a version like this, like a New American Standard, okay? Are we supposed to use the Jehovah's Witness version? Because they say it's the only word to use. Okay, there are many different people that say this is the only version you're supposed to use. Okay? So no. Okay. So then he says, you don't know how mediometric dating works. OMG, son, the dates are arbitrary, or the dates are arbitrary or random. And I said, yes. Thank you. Yes, they are arbitrary and random. I think he meant to say the dates are not arbitrary or random. Then he says, I do understand radiometric dating in science. They run tests with different samples and run different methods of dating. If everything says 65 million years, for example, and one says 100,000, then the 100,000 years is wrong. It's not how it works, son. Okay? Believe me, I know. Because a guy actually went through my comment section, I believe it was on the first Simon Dan rebuttal video, and tried to put in a whole bunch of stuff on how radiometric dating works. Okay? And basically, they don't get everything says 65 million years. Because they use a thing called a mass spectrometer. Okay? The mass spectrometer just measures the amount of molecules. And then they count with each sample. Okay? And so they test like 10 times. Okay? And they get 10 different numbers. What they look for is they look to see which numbers are closest to the ones that they want. And then they circle those numbers and they say, see, sample 3, 5, and 8 gave us close to 65 million years. So we know that it's 65 million years. No, you don't. Okay? That's why you'll see in scientific papers where they say, oh, this sample dated it at 65 million plus or minus, 35 million. Because they take all the other numbers, okay, and they throw out what they call the outliers, which are the samples that are way above or way below their numbers. They throw those out completely. The rest of the numbers, they basically just sit there and they go, well, yeah, it gives us plus or minus 35 million years. Because they average it, and then they say that's how much. And then they subtract that average from their what they think is known age. Because they use the index fossil to tell them what the date should be. Okay? And then they count the rock layers to verify that the index fossil that they see is in the same rock layer. They literally use the rock layers. They don't necessarily use potassium-argon dating or carbon-14 dating. Okay, carbon-14 dating is actually only accurate to about 50,000 years. Okay, because by then the amount of C14 that's supposedly in the sample has decayed past the point where you're not going to be able to measure any molecules off of it. Okay, the potassium-argon dating, the reason why they say it's accurate to like billions of years, is because potassium is supposed to have a half-life, radioactive potassium is supposed to have a half-life of like 500 million years or something like that. Okay? And that's why they say, oh, it's accurate to this many billions of years. But then they don't think that there might be radioactive potassium in the earth right now. They think, oh no, it came when it was shot up by some flood, some lava flow long ago and far away. That's when it gained all the radioactive potassium. And then it decays into argon. Well, that's a big assumption. That's how radiometric dating works. Okay? So, no. Everything doesn't say 65 million years and then one part of the sample says 100,000 years. That is a misnomer. That is an ignorant statement. That means you have next to zero idea of how a mass spectrometer works. I've actually used a mass spectrometer. In fact, in my I6 course at my technical college, my Instrumentation 6 course, which was the last part of the course, I actually had to give the presentation on how mass spectrometers work. So when this guy comes in with all these charts about how all this stuff works, I'm like, dude, you're literally talking about mass spectrometers. I know how mass spectrometers work. Okay? I've used them before. And basically, all you're trying to say is that, yeah, we basically counted the amount of molecules. Okay? Because if the sample is supposed to be 65 million years old, because we got it out of the 65 million year old rock layer, okay, then we only take the numbers that are around 65 million years. And then we use some of the other numbers to try to get an average. And they throw the rest out. They throw out 90% of the numbers to get the numbers that they need. Okay? To say 65 million years, plus or minus 35 million years. In fact, Ken Hovind, in one of his presentations, one of his slides that he has, is this one was like, it's like 300,000 years old, plus or minus 300,000 years. Do you know what that error factor is? That is an error factor of 200%. Because you're 100% on either side. You can't have that in statistics and call it like we know. That is, we have no idea. Because the samples that we looked at are completely wrong. Okay? So, son, Turbo Brain, son, you are way off. Way off. You have no idea what you're talking about. Okay? You have next to no idea what you're talking about. Because in the real world, it doesn't pop up with, oh, here's 65, 65, 65, 65, 65, 65, 65. Oh, and then there's one down here that's an outlier that's 100,000 years. If they had a dating method that was that accurate, believe me, there would be a lot less Christians on the earth today. But the sheer fact that they come in, okay, and they go test potassium argon from a 20-year-old eruption, Mount St. Helens, and they get hundreds of thousands of years on their potassium argon dating, means there is something wildly wrong. And there are so many people that are like, oh, well, you just don't understand that, it's like the crust gets sucked underneath and, that crust is probably really old and blah, blah. No! That doesn't matter. Because the mantle itself would burn off a lot of that argon. Okay? It would break up a lot of those molecules because the heat of the mantle is intense. That at that stage, a lot of that radioactivity speeds up. Okay? That's literally what they do in a nuclear reactor. My dad worked in a nuclear reactor for 25 years. He literally got a degree in nuclear engineering. Okay? And he explained to me, because I kept asking him, because they would have these outages where they had to replace the fuel rods. And I'm like, why do you have to replace the fuel rods? And he's like, because when we take the plutonium, because we take zirconium blanks, we bombard them with hydrogen atoms. Okay? And basically what we're doing is we're basically building from zirconium up to plutonium. We're basically bombarding the atoms, individual atoms. We're making them heavier, okay? We're artificially making them into plutonium. And then what we do is we stick those plutonium rods down into the core. And that core literally heats up and it excites those molecules. And what it does is that core heats up to a temperature to where the amount of radioactive decay speeds up. So normally, if you were to just take radioactive plutonium, okay, or let's say uranium, and you were to just set it out, and you just let it go, okay, uranium just goes. Like the neutrons just go. And that's what you're measuring with a Geiger counter, okay? So when you stick a Geiger counter out there, and you hear it, and it's like, when you get close to a thing, it's because it is measuring the amount of neutrons that are coming off of that. Like if you just had a chunk of uranium, right? Okay? I mean, you couldn't hold it in your hand. But let's say I could. Okay? Let's say I could hold uranium in my hand. Okay? And I had a Geiger counter right here. And it was just going. It would be going like crazy because there's so many neutrons that are flying off of that uranium. That's what we call radioactivity. Okay? It's the neutrons don't want to stay connected to the molecules. They start flying away. Okay? And every once in a while, protons will leave, okay? And eventually, what ends up happening is, okay, is that uranium eventually breaks down. Because enough of those neutrons leave, all that's left are the protons. And those protons basically become inert. Okay? They don't move, they don't do anything. Because the neutrons are gone. Call that lead. Okay? It basically becomes lead. Now with plutonium, okay, what they did is they took uranium and they figured out that if they could bombard the uranium atoms, or the uranium, with something like hydrogen, which only has one proton and one neutron on it, they basically could bombard that molecule, okay? And that formless lump, okay? Or that lump of uranium. They could enrich it, okay? And it would make something called plutonium. They called it plutonium after the 9th planet, Pluto, okay? I know people are like, Pluto's not a planet. It's a planet to me, damn it. Because when I grew up, it was a planet. It's still a planet. It's always going to be a planet to me, okay? They named it after Pluto, okay? Plutonium. Because they discovered that when they created a symmetrical explosion around a lump of plutonium, okay, it basically forced the atomic bonds to implode, which actively broke the atomic bonds holding them together. And those atomic bonds would then send those neutrons into overdrive. It's an atomic bomb. Okay? It's boom. We're doing the same thing inside a nuclear reactor. Much more controlled, because what we're doing is we're lowering those rods in. Okay? The rods are actually already in place. What we do is we lower the rods in, okay, and then you have these control rods. And what the control rods do is that they actually absorb neutrons. And what you're doing is you're basically, you have a channel, and what you do is when you stick the rod inside the channel, it forces the neutrons to bounce back in on themselves and hit more neutrons coming this way. And what that does is that generates friction, which generates heat. And that heat excites. And we make steam. We basically boil water with it. Okay? It's a very efficient way. But it breaks down. Okay? That's what I'm saying. If I had a lump of uranium sitting in my hand, okay, that uranium would just be giving off neutrons. And if I put a Geiger counter next to it, okay, that's what it does. So if you heat up the uranium, if you were to heat up that uranium, its half-life would speed up tremendously, because you are exciting more molecules on the inside and you are releasing more neutrons. And if you contained that inside of a sphere of some kind, that would cause those neutrons, again, to bounce and come back. And so the more neutrons that you have coming out, the more neutrons you have going back in, the more excited they become. Okay? And the more heat is given off. And the point is that if you have a subduction zone, like you have on the west coast of the United States, okay, where you have the Juan de Fuca plate subducting under the North American plate, okay, eventually what ends up happening is that stuff goes down into the mantle and it reheats. Melts down, becomes magma. What is magma? Superheated rock. Okay? And then what happens is that superheated rock wants to find a way to the surface. We call those volcanoes. Okay? So, if carbon dating was accurate, I'm not carbon dating, but if radiometric dating was accurate, okay, then all of that radioactive potassium, okay, would actually speed up. But it would burn off the argon, okay? Or the argon would become radioactive potassium once again, because more molecules would get attached to the potassium, and then when it exploded out, the argon would be gone and the potassium would be there, okay? So you would think that if it exploded up into the air, like, let's say, I don't know, Mount St. Helens, okay, it exploded up into the air, then you would be able to test that, and it would say, you know, you would get way more potassium molecules than you would argon molecules. Okay, that's all I'm saying. Because here's the assumption that radiometric dating runs on. Okay, and then we'll end this, because I know it's been about an hour, almost an hour. Basically, the point I'm trying to make is that the main assumption that radiometric dating runs on is that there's only parent isotopes. There are no daughter isotopes. Or very little daughter isotopes. Okay? There's like a ton of parent isotopes, little to no daughter isotopes. And then after a certain amount of time has passed, that there is more daughter isotopes than there are parent isotopes, because they have decayed into the daughter isotope. So if we had uranium-235, after a certain amount of half-lives, okay, after a certain amount of decay has happened, it becomes lead. So if you had more uranium atoms than lead atoms, then it's not as old as if you had something that had mostly lead and no uranium. That's the assumption that they run on. But what is in our atmosphere? Our atmosphere actually contains carbon-14. It contains argon gas. Okay? It's not as easy as it looks, because these people are running on the assumption that our atmosphere doesn't affect anything. But I'm here to tell you that if you've eaten plants, you have carbon-14 in you. Okay? You're breathing it in. You're breathing it out. That's CO2. It's trace amounts, but it's there. Because the amount of C14 in our atmosphere is continually increasing. It has not reached equilibrium yet. And the assumption when they first discovered carbon-14 dating was, they just said, well, the Earth is billions of years old, so we can ignore the equilibrium problem. So they completely just bypassed the fact that C14 was still building up in our atmosphere. We haven't reached equilibrium yet. That's the problem. Actually, okay. I'm going to read one little passage, and then I'll do my outro, and we'll call it an episode. And because it's close to Christmas, I think you know what I'm going to read. Now in those days a decree went out from Caesar Augustus that a census be taken of all the inhabited earth. This was the first census taken while Quirinius was governor of Syria. And everyone was on his way to register for the census, each to his own city. Joseph also went up from Galilee, from the city of Nazareth to Judea, to the city of David, which was called Bethlehem, because he was of the house and family of David, in order to register along with Mary, who was engaged to him and was with child. While they were there, The days were completed for her to give birth, and she gave birth to her firstborn son, and she wrapped him in clothes and laid him in a manger, because there was no room for them at the inn. And in the same region there were some shepherds staying out in the fields, keeping watch over their flock by night. And the angel of the Lord suddenly stood before them, and the glory of the Lord shone round about them. Then they were terribly frightened. But the angel said to them, "Do not be afraid, for behold, I bring you good news of great joy, which will be for all people. For today in the city of David there has been born to you a Savior, who is Christ the Lord. This will be a sign for you. You will find a baby wrapped in clothes and lying in a manger." And suddenly there appeared with the angel a multitude of the heavenly host, praising God and saying, "Glory to God in the highest, and on earth peace among men with whom he is pleased." When the angels had gone away from them into heaven, the shepherds began saying to one another, "Let us go straight to Bethlehem then, and see this thing that has happened, which the Lord has made known to us." So they came in a hurry, and found their way to Mary and Joseph, and the baby as he lay in a manger. When they had seen this, they made known the statement which had been told them about this child. And all who heard it wondered at the things which were told to them by the shepherd. And Mary treasured all these things, pondering them in her heart. Turbo Brain, if you watch this to the end, I'm praying for you, man. I really am. Your ignorance is astounding to me. And I'm praying that God opens your eyes. That you finally understand that us Christians are not crazy. And that a little over 2,000 years ago, a baby was born to a virgin. And he wants to know you. His name is Jesus. I hope that you actually pick up a Bible. And I pray right now that the Holy Spirit comes down and shows you the truth. Merry Christmas, everybody, and have a Happy New Year. Smash that like button, hit subscribe, drop a comment below. Let me know what you think about this. I know my lighting's been a little funky. I'll have it all fixed by next year. I might be doing another couple episodes before that, but you know, I'm gonna try to get it fixed before next time. Okay? And so, as we like to say, we will see you on the next one.